Hey guys, welcome back. So let's do another example of hierarchical clustering. So this tutorial will serve as a very good introduction to the hierarchical clustering method. So we will see what packages we need. We will see what hierarchical clustering algorithms are. Then we will see how to prepare the data. Then we will see the hierarchical clustering with R. All right. Then we will see how to work with dendrograms. Then finally we will determine the optimal clusters. Okay, so for this we need the packages like tidyverse, so which is used for data manipulation, and we need cluster package, so which is for clustering algorithms. Then we need facto extra. Okay, facto extra is a library for clustering visualization. Then we need the dend extend, which is for comparing two dendrograms. All right. So as you know that hierarchical clustering algorithms are agglomerative and divisive. So agglomerative is also known as AGNES, means agglomerative nesting. It works in a bottom-up manner. That is, each object is initially considered as a single element cluster, and at each step of the algorithm, the two clusters that are the most similar are combined into a new bigger cluster to form the nodes. This procedure is iterated until all points are members of just one single big cluster that becomes the root. Okay. The result is a tree which can be plotted as a dendrogram. So you can see the libraries are working. If you haven't installed them, go ahead and first install them, then you can load the libraries. Then the second type of hierarchical clustering is divisive. It's also known as Diana, means divisive analysis, and it works in a top-down manner. The algorithm is an inverse order of Agnes. It begins with a root in which all objects are included in a single cluster. At each step of iteration, the most heterogeneous cluster is divided into two. The process is iterated until all objects are in their own cluster. All right. So first we will have to prepare the data. So the rows are prepared as observations and columns as variables. Any missing value in the data must be removed or estimated. The data must be standardized to make variables comparable. Recall that standardization consists of transforming the variables such that they have mean 0 and standard deviation 1. All right. So here in this example, we will use the built-in R dataset US arrests, which contains statistics in arrests per 100,000 residents for assault, murder, and rape in each of the 50 US states in 1973. It includes also the percent of the population living in urban areas. So first let's load the US arrests dataset. So df equals us arrests. Then to remove any missing value that might be present in the data, we need to use the omit function. So df equals na dot omit of df. So as we don't want the clustering algorithm to depend to an arbitrary variable unit, we start by scaling or standardizing the data using the R function. So let's use this scale function and print the summary. So this scale function will give us the output. So df equals scale df, then we'll print the summary. So let's see how it looks. All right. So this is a summary of the data frame. So have a look at it. So we installed the libraries, then we loaded the libraries. All right. Then we imported this US arrests dataset. Okay. Now let's see this hierarchical clustering with R. So there are different functions available in R for computing hierarchical clustering. So the commonly used functions are hclust, which is available in the stats package, and Agnes in cluster package. So these are for agglomerative hierarchical clustering, and Diana. So this is in cluster package, which is for divisive hierarchical clustering. So first we will see agglomerative hierarchical clustering. We can perform agglomerative hierarchical clustering with hclust. So first we compute the dissimilarity values with dist and then feed these values into hclust and specify the agglomeration method to be used. That is complete average single ward.d. All right. Then we can plot the dendrogram. Okay, so D equals dist of df comma method equals Euclidean. So this is the dissimilarity matrix. Then hierarchical clustering with complete linkage. So hc1 equals hclust of D, method equals complete. Then we will plot the obtained dendrogram using the plot function by passing hc1 as the argument. So this will show us the dendrogram. Right. Okay. So here we got the dendrogram. So have a look at this output. Okay. So alternatively, we can use the Agnes function. So these functions behave very similarly. However, with the Agnes function, you can also get the agglomerative coefficient, which measures the amount of clustering structure found. So let's use this Agnes function now. So HC2 equals Agnes df comma method equals complete. Then let's print this. So first we are computing with Agnes here. Then we will print the agglomerative coefficient HC2 $AC. So the coefficient here is 0.8531583. So this allows us to find certain hierarchical clustering methods that can identify stronger clustering structures. So here we see that Watt's method identifies the strongest clustering structure of the four methods that have been assessed. All right. So let's proceed and see the methods to assess. So we have average, single, complete, word. Okay. Then names of m equals c of average, single, complete, word. Now we will see the function to compute the coefficient. So AC equals function of x. Then we will use this Agnes function. Agnes of df comma method equals x $AC. Then we will use this map dbl function and pass this m and AC. So let's run this. We will get the coefficient for each of these methods. Okay, so this is the output. Then we will run this AC function. Then we will call that function. Okay, yes. So let's do it again. Okay, so this is the coefficient for each of the functions: average, single, complete, and word. So similar to before, we can visualize the dendrogram. So let's try to write the code for creating the dendrogram. hc3 equals Agnes df comma method equals word. Then we will plot this tree. hc3 cex equals 0.6, hang equals -1, main equals dendrogram of Agnes. Okay, let's see how the new dendrogram looks. Okay, so this is the dendrogram using the word method, all right, and calling the Agnes function. So have a look at it. Okay, so next we will do the divisive clustering, divisive hierarchical clustering. So here we will be using the R function Diana. The R function Diana provided by the cluster package allows us to perform divisive hierarchical clustering. Diana works similar to Agnes. However, there is no method here to provide. So let's first compute divisive hierarchical clustering by using the Diana function. So HC4 equals Diana of DF. So this is to compute divisive hierarchical clustering. Okay, then the divisive coefficient among the clustering structure, we will print it HC4 $DC. Then we will plot the dendrogram. HC4, CX equals 0.6, hang equals -1, main equals dendrogram of Diana. Okay, let's see the output. Okay, so this will give us the coefficient now, that is 0.851435, right, which we had got it. All right, then let's see the graph, the dendrogram. Okay, so this is the dendrogram using the Diana function. So let's just have a look at it. All right, let's continue. So now let's see how to work with dendrograms. So in the dendrogram displayed above in this program, each leaf corresponds to one observation. And as we move up, the three observations that are similar to each other are combined into branches which are themselves fused at a higher height. The height of the fusion provided on the vertical axis indicates the dissimilarity between two observations. The higher the height of diffusion, the less similar the observations are. So note that conclusions about the proximity of two observations can be drawn only based on the height, where branches containing those two observations first are fused. We cannot use the proximity of two observations along the horizontal axis as a criteria of their similarity. The height of the cut to the dendrogram controls the number of clusters obtained. It plays the same role as the K in k-means clustering. In order to identify subgroups, we can cut the dendrogram with cut tree. All right. So in this session, we saw working of divisive hierarchical clustering and mainly the agglomerative hierarchical clustering. So in the next session, we will see how to work with dendrograms. We will continue with the same example and see how to work with the dendrograms. All right. So we will see different methods. We will see different dendrograms. All right. Then we will try to determine the optimal clusters using different methods. All right. Okay. So any queries you have, you can write to us. Thank you.